Hello, and thank you for joining us. Today's presentation is Basic Principles of LA-ICP-MS and Uranium-Lead Geochronology. Today, our guest speaker is David Chu. David Chu is a professor in the Department of Geology, Trinity College Dublin. He studied geology at University College Dublin, obtained his Bachelor of Science in 1996, and his PhD in 2001. From 2003 to 2005, he was a postdoctoral researcher at the University of Geneva. He returned to Trinity College Dublin in late 2005 to take up a lectureship. He lectures in the field of structural geology and tectonics, while his research interests involve applying geochronology and thermochronology to a variety of problems in the geosciences. We will be taking questions, so please feel free to submit questions throughout the presentation and we will answer them at the end. This presentation is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, David Chu.
Thank you very much for the introduction. So what I'm going to talk to you today is latest developments in uranium-lead LA-ICP-MS geochronology. And many of the slides and many of the things I'll be talking about are things that have been developed in our own lab in Dublin, but these techniques are also independently being developed in many labs around the world. So let's move on and let's have a look maybe at a brief introduction to how LA-ICP-MS works and how uranium-lead geochronology works before I show you some of the latest developments. So how does an LA-ICP-MS system work? Well, our sample, which in the case of geochronology is normally a 25mm puck, or sometimes a thin section, is placed in a sample holder, which is then put inside a laser ablation cell, which has got a helium atmosphere. And our laser ablates through a glass window. It generates an aerosol once it hits the sample, and this is transported through tubing into the plasma torch. Argon gas is being fed into the plasma torch, and there's an RF coil wrapped around the plasma torch, which induces a plasma and it ionizes our sample, which is then transferred across the cone interface of the ICP into the high vacuum part. It's focused by an ion lens, and then a quadrupole mass analyzer selects a given mass charge ratio where it's analyzed by a detector. And in our system in Trinity College Dublin, we use an Agilent 7900 quadrupole ICP-MS system, and this is our photon machines laser, which we purchased, I think, in 2012, still going strong. It's an analyte X-site. And in conventional uranium-lead geochronology, we undertake something known as a spot ablation, where the laser is ablating the sample. The sample is not moving underneath the laser, so we're progressively making a deeper and deeper pit. And if we look at a time-resolved analysis of a spot ablation, you can see that we start off high, and then all the various isotope signals decrease as we progressively ablate down into the laser pit. And now, a quick uranium-lead dating primer. So uranium has two isotopes which are radioactive. There's 238 uranium, which decays to 206 lead, with a half-life roughly equal to that of the solar system, about 4.5 billion years. And then 235 uranium, which decays to 207 lead, with a half-life of around 700 million years. There's also another isotope of lead, 208 lead, produced by the decay of thorium-232, and also an isotope of lead that's not radiogenic. It's not produced by radioactive decay. It's left over from the formation of the solar system, and it can be used as a monitor of the initial amount of lead, also known as common lead, in a crystal. And this is 204 lead. But what makes uranium-lead geochronology so powerful is that we have two independent decay schemes, 238 and 235 uranium decaying respectively to 206 lead and 207 lead. Now what you can do is you can make a diagram called the Weatherall Concordia. And on the y-axis you plot the 206 lead, 238 uranium ratio. On the x-axis, the 207 lead, 235 uranium ratio. And you can make a curve, which is the locus of points, such that these ratios give the same age. And this is the Weatherall Concordia. So on the right-hand part of this diagram, there's a zircon. And we're going to do a spot ablation on the rim of this zircon. You can see it's got an oscillatory zoned outer rim. And it's about 1.5 billion years old. It's concordant, it plots on the Weatherall Concordia, and everything is fine. But you can see inside this cartoon zircon, there's also, if you like, a very discrete discontinuity inside the crystal. And this is an older inherited core. Zircon is quite a refractory mineral that's able to survive multiple episodes of sedimentary recycling and also even survive inside a magma chamber for a while. So maybe this zircon, the rim of which grew in a granite, has an older core. And this older core was floating around in the granite magma. And if we place the spot on that, it's much older and it's giving an age of around 3.5 billion years. And then let's imagine now that we had an imperfectly placed analysis, and it might mainly be, for example, core with a small bit of rim, but it's going to be a mixture between these two components. And similarly, if we've got a rim analysis with a small bit of core, it's going to plot closer to the 1.5 billion year old rim. So these analyses, what they're doing is they're making a mixing line, which is called a discordia between these two age components. So because we've got two decay systems, we can see, for example, the systematics of how the zircon is behaving. We can also have discordias for other reasons. For example, we might have our 1.5 billion year old zircon, and then we start to, maybe recently, we heat the zircon up, say in an orogenic belt, or it falls into a magma, and we start to lose some of the radiogenic lead inside the crystal. And that will give us a mixing line towards the common day, which is effectively the origin of this graph. So recent lead loss would drag us in this direction. Or let's imagine that our zircon had variable amounts of lead at the time of crystallization. And in this case, what we have is we'd have a discordia plotting out towards common lead. So you can move around in Concordia in a variety of different ways, and precise laser ablation ICP-MS targeting of different components can help resolve these issues. Minerals that don't contain initial lead or common lead at the time of crystallization would be minerals such as zircon and monazite. So in terms of uranium lead dating, these don't require common lead correction. However, many minerals that we target in uranium lead geochronology do contain initial lead. These include titanite and rutile, where the standard materials often don't contain initial lead, but unknowns often do. And then apatite, alunite, and calcite. Apatite and calcite, for example, even the standard materials often can contain appreciable common lead, which has to be corrected for. So we're able to date a variety of different phases by uranium lead geochronology. So let's move on to some applications. So for over 2 decades, we have been able to date the crystallization age of magmatic and metamorphic rocks, particularly the mineral zircon, by LA-ICP-MS. Spot sizes have decreased with time as both lasers become more efficient at transporting the aerosol, and also as ICP instruments become more sensitive, so less analyte is required. But this is a fairly typical application, fairly standard, and apart from decreasing spot sizes, maybe there hasn't been a huge amount of developments in that particular aspect of LA-ICP-MS geochronology. But recently, people are undertaking more and more sedimentary provenance studies, which involves dating different mineral grains in sands or sandstones to infer where the source of the sand or sandstone was. If you know something about the uranium lead systematics of the source region, its characteristic uranium lead age signature, then you can infer where the sand came from. But to do this, and to be statistically reliable, you really need to have large data sets, comfortably larger than 100 grains per mineral phase dated. And this is where some of the recent advances in laser ablation, ICP-MS, are really coming to the fore, the ability to rapidly produce large data sets. So some of the things that we do in our lab is we do multi-proxy sedimentary provenance studies. For example, we look at the mineral rutile when it's present in the heavy mineral fraction. Rutile dominantly forms in high-pressure metamorphic rocks, occasionally some igneous rocks. Zircon forms in granites and other silica-rich magmatic rocks, but also sometimes in high-grade metamorphic rocks as well. And then apatite, calcium phosphate, and it forms in both granites and gabbros, and also a whole variety of different metamorphic rock types. So these minerals are all telling us something slightly different. They have different fertility in different rock types. Rutile is more present and more common in high pressure rocks than other rock types. Zircon is not found often in basic rocks. We can also exploit the different temperature sensitivities of these minerals. For example, apatite records the temperature or the time at which the rock hosting the apatite last cooled below about 450 degrees, whereas zircon has a very high closure temperature and nearly always records crystallization. And one of the things that ourselves and other labs are increasingly doing is that we're dating large amounts of grains in the heavy mineral fraction that have previously been identified by either SEM, EDS, or Raman approaches. So this slide down here is from our photon machines laser. It's been imported into our photon machines laser. And these are all the various analysis points that were identified by Raman. You can see the 5 reference coordinate points. So these enable us to bring this image into our laser software. And we have thousands and thousands of analytical XY points where we can find all the zircons, all the monazites, all the rutiles, and then go ahead and date them in extremely large sessions. And if we zoomed in on just one of these little samples here, so this might be several hundred grains in this sample, you can see that all the various grains are individually numbered. They've been previously identified by Raman. So armed with these large data sets, we can then start to say something more diagnostic about provenance determinations in sedimentary basins. So this example I'm going to show you is from a carboniferous basin in Western Ireland. It's predominantly a Pennsylvanian basin in Western Ireland, and it's got potentially a large amount of sources, the Laurentian continent, then portions of Gondwana, these small terrains off the margin, Gondwana, Avalonia, Cadomia, Armorica, and so on. And we undertook zircon, uranium-lead work on these rocks, and also apatite, uranium-lead work on these rocks, and you can compare the age spectra. The apatite is predominantly young with very, very minor amounts of old detritus, whereas the ability of zircon to be recycled means that we have many more substantially older age peaks. And most of the detritus seems to have, for example, a Laurentian source, but there is some input from Gondwana as well. And one of the things that we've been looking at is how we can integrate apatite, uranium-lead age, and trace element information into detrital zircon data sets. So for example, we can see that if we looked at this Caledonian peak, which in the zircon is about 430, the apatite peak's maybe about 30 million years younger. And that's because apatite is recording the cooling of these Caledonian granitoids, and the zircon is recording the crystallization age of these Caledonian granitoids. And we also simultaneously acquire trace element data when we acquire our uranium-lead apatite ages. And we can put these onto provenance determinant diagrams where we're able to identify the various types of rocks that these apatites crystallized in. So for example, there is 2 fields here, high-grade and low-grade metamorphic rocks, HM and LM. So there's a large amount of low-grade metamorphic apatite detritus. And then we can identify potentially 4 different igneous fields, alkaline igneous rocks, which are marked here, and then intermediate I-type magmas, S-type magmas, and ultramafic magmas. So we can combine all this information give much more diagnostic provenance determinations. And another thing that we've been experimenting with is trying to speed up analyses, uranium-lead analyses. So one thing that we've been doing is we've been availing of the Photon Machines ARIS, the aerosol rapid introduction system, because this gives very fast washout. So when we're doing a spot analysis, when we couple this onto our system, we don't get smearing between different age domains. For example, in a zircon analysis, if we use a high repetition rate. So we tried this at repetition rates up to about 50 hertz. And the ARIS means that we're not going to smooth in the age information as we go through different age components. And we applied this to a meta-sandstone from Northwest Ireland. It's actually a cryogenian glacial rock, where we really would like to know the age of this rock. And what this approach, using very rapid spot dating, where it's taking about 5 seconds per analysis, is that it means we're able to screen the zircon population to try and find the youngest zircons in the sample. So in this particular sample, including standards, we were able to analyze over 1,000 zircon unknowns in less than 3 hours. And we get a uranium-lead detrital zircon age spectrum. And we can see that there's a very small minor peak, which is the youngest peak present in the sample. It's around 700 million years old. And this peak, which is defined by only 3 grains out of 1,000, helps us constrain the age of the rock. We know that the rock has to be younger than that particular peak. So it gives us a maximum depositional age. The maximum depositional age of this sample is 700 million years. But if we were just doing a conventional speed analysis, it would take us a long time to analyze 1,000 grains. So this population is about 0.3% of the overall total grain population. I'm now going to move on to laser ablation ICP-MS trace element mapping. So we've been applying this technique recently to geochronology. First of all, I'm going to show you an example of how this technique has been used to look at the trace element content of igneous phenocrysts, a paper by a colleague, Teresa Vede, which came out in 2015. So the idea is that we find a phenocryst that we want to map. Here's the phenocryst there. And it's a kleiner peroxide. And we're going to scan the laser across the sample, like so, constantly acquiring time-resolved trace element data. So the image is built up of a series of line scans or rasters, like so. It might take maybe half an hour to an hour to acquire an individual image, but we're constantly working and trying to make these things faster. And you can see if we had looked at one of these line scans under the SEM, you can see the pattern of the successive laser spots overlapping each other. And then we can stick this into our laser data reduction software, and we can generate images. And we now use the ARIS, the fast washout laser ablation cell, to do this. And in this particular study, it was employed to look at the histories of kleiner peroxine and hornblende phenocrysts in terms of their crystallization history. Were they showing normal magmatic fractionation trends, or did they also show pulses of mafic recharge from looking at transition elements such as maybe chromium or nickel or scandium? And we do see that there's pulses of mafic recharge in these volcanic systems. Another application I'm going to show you is looking at trace element mapping of olivine. So this is a paper again by a colleague from 2017, Claire Stead. And in it, she was looking at olivine with the goal of trying to see if the rare earth elements in olivine behave according to crystal lattice strain theory. So here's an Enuma diagram, partition coefficients on the y-axis and cationic radius here on the x-axis. And you can see this deviation of the light rare earths off the Enuma trend. And why is this caused? Well, one of the reasons is that it could be analytical, because the light rare earths in olivine are present at concentrations of around 10 to 30 parts per billion. Yet that is really tricky to measure by just about any analytical technique. It really is ultra trace element mapping. And so this experiment was using 30 micron spot with around 60 hertz over a 5 by 5 micron area. And you can see the various stages. Here we have plagioclase, so it's on the aluminium map. It's got lots of aluminium. And then the olivine is in here and in here. And I'll highlight the olivine now in green. So what we're going to do in the next screen is we're going to see what happens in the post-data reduction stage when we interrogate an LA-ICP-MS map using the iolite software. So we're going to go from the plagioclase into the olivine and see what the light rare earth element characteristics are. So let's move on. Okay, so here, what I'm going to do is I'm going to show you a traverse going from here, from the plagioclase into the olivine, and then going back out into the plagioclase. And there's going to be a live rare earth element viewer panel here activated, which is normalized to chondrite. So you can see that the plagioclase is light rare earth element enriched, and it has a positive europium anomaly. And we would expect to see, once we get into the olivine, something looking more like this. So, move on. And the plugin for iolite that is used to interrogate these data is called Monocle. It's written by Joe Petris in 2017. Okay, so hopefully this now brings up the, there it is, there's the cursor. I'm following the cursor with the PowerPoint laser pointer so you can see what's happening. And you can see how the light rare earths are going higher when we're in the plagioclase, and then they decrease when we go into the olivine. Let me just do that once more. Okay, let's look at that there. You can see now we're getting light rare earth depletion in the olivine, and then it starts to increase as we get close to the plagioclase rim. And the reason is that we have light rare earth element diffusion on the borders of the olivine close to the plagioclase, which is effectively affecting our primary light rare earth element contents in the olivine. And if you were doing conventional spot ablations, the analysis would be completely compromised. So laser ICP-MS mapping is the best way of trying to work out detailed light rare earth element systematics, such as in this sample. It gives you far much more information, and you've got a spatial context. We started applying this to geochronology. So that we did in 2017, looking at a zircon, which has two age components. There is a rim, which is CL dark, cathodoluminescence dark, and then there is it's high in uranium, which is what you'd expect. CL dark was high in uranium typically. And then a more CL bright oscillatory zone core, which is lower in uranium. On a Raman map, looking at a certain waveband, we can see that these zones here, if we looked at the Raman spectra, would be very metamixed because they're so high in uranium, whereas we've got pristine, less damaged zircon in the core because it's got lower uranium contents. We can see how the core rim boundary is nicely picked up by the thorium-uranium map. We must have had lots of thorium potentially in the outer parts of the core. But what's particularly nice is that you might be able to make out fractures in the cathodoluminescence image. I'll highlight them now in red. And if we were to look at the uranium lead age map from this grade, we can see that those fractures still exist. We've got younger ages where the fractures are. So we've got lead loss in the fractures, and I'll highlight them there. So we're able to really characterize the crystal in extreme detail. We can even take portions of the analysis, 4x4 pixel blocks, and plot each of these 4x4 pixel blocks onto a concordia, and we get the two age components and some mixing in between the two, and it satisfactorily picks out the 1.1 billion crystallization age of the core, and also the 480 million year old crystallization age of the rim. And finally, the last thing we've been trying laser ablation ICP-MS imaging to is uranium lead dating of carbonates. So this is a an approach which has got a variety of different applications, such as dating veins, diagenetic cements, dating limestones which are non-fossiliferous, such as in the Neoproterozoic, and also dating veins or carbonate-hosted ores in, say, for example, Mississippi Valley-type ore deposits. But carbonates, for example, calcite, contains really small amounts of uranium, probably 1,000 times, 3 orders of magnitude less than zircon. It also has a relatively substantial amount of initial lead, and this can generate unfavorable uranium-lead ratios and large resultant age uncertainties. So this is the approach that we've adopted. So we choose a portion of the sample, often by earlier petrography, and then we perform a laser ablation ICP-MS rastering over the sample to generate both trace element and simultaneous uranium-lead age maps. And then we're able to interrogate these data using the Monocle plugin for iolite. So for example, we've done using a script-based plugin for Monocle. We are telling the computer to only choose pixels which have a rubidium value of less than 0.5 ppm. Rubidium is commonly present in both clay minerals and metamorphic micas, igneous micas. So it's a good way of stripping out any clay or diagenetic cement out of your sample. And then we're only interested in portions of the sample which have got small amounts of magnesium. In other words, the sample hasn't been dolomitized. So we can stick in those two criteria, and we end up choosing a certain portion of the sample, which is this portion here. And that corresponds to this region here. And it's got a nice variety or range in uranium-lead ratio. A high uranium-lead ratio portion here. Sorry, that's actually a 206 to 238. So that's the other way around. So this portion here is high uranium and low lead, and likewise, this here is the converse. And what we're able to do then is we choose all these pixels that meet these criteria of rubidium and magnesium concentrations, and we're then going to tell the computer, I want to make analyses out of this. So we want to split it up on uranium-lead ratio, and then we can plot these analyses on Terra-Wasserberg Concordia. So these are different uranium-lead ratios, and then we can get a much, much more precise and well-constrained Terra-Wasserberg isochron, with the lower intercept giving the crystallization age of our carbonate, and the upper intercept giving us the initial 207 lead, 206 lead constraint. So I think that concludes my presentation, and I am very happy to take any questions from members of the audience.